Normally we'd always expect the downward force coming from the self-weight of the structure or from snow loads or that sort of thing, going in the same direction as gravity. But with this canopy, if you get wind collecting underneath the roof, you may get an upwards force from that wind that cause uplift on the structure. So the case of uplift is the reason we don't have a structure that looks like this with a flexible cable instead of the sort of more rigid member. Because when you apply an upwards force to this structure, it just fails. The cable has no resistance to compression. In this case, you see, when you apply an upwards force, the roles of these two members can be reversed. So the upwards force is resisted by compression in this diagonal member, which has a vertical component resisting that applied force and a horizontal component of compression as well. And that horizontal component is resisted by this horizontal member going into tension. So we're going to look at the canopy structure, and we've got two arches spanning to opposite sides of the canopy. And I'm going to assume these arches are actually 3-pinned arches. So you do have a connection at the top of the structure, and 3-pinned arches have some advantages over 2-pinned arches. Firstly, they're statically determinate. So we can work out the reaction forces just using simple static equations. The other reason they're good, potentially, is that they can be easier to construct than 2-pin arches, because you can construct separate sides of the arch individually. So what we have here is a pin at the top and a pin on either sides, and these are all going to allow rotation. So let's apply a load and see how it's going to resist the force. So we're going to assume that we apply a point load to the top of the structure. Probably in a normal loading case, you'd have a uniformly distributed load or something similar, but a point load will be easy to analyze for this, and it gives roughly the same sort of ideas. So when you apply this load, you can see the deformation, the structure is moving downwards at the center, and it would be easy to imagine if you moved lateral restraint away from these supports, you get a deflection going outwards. So from this we can infer that there's going to have to be an inwards horizontal force, a reaction force, resisting that thrust on both sides of the arch. And also, to balance the vertical forces, we're going to have an upwards vertical reaction force. So let's look at how this affects the moments on the arch. Now, if this was just a beam, you can see that the moments would increase linearly as we move away from the support, because the lever arm of this vertical force would increase linearly. But as we move along the arch and continue taking moments, you'll see there's actually two reaction forces which are going to contribute to the moment experienced at the cut. And you can also see, I hope, that they're moving in different directions. So one's going clockwise and one's going anti-clockwise. Now, we know that the vertical forces are going to be the same as on an equivalent beam. So what this shows us is that these horizontal reaction forces resisting the thrust are going to have the effect of decreasing the moment in comparison to a similar beam. And this is the reason why an arch has been chosen, because for the same span, the same loads, you get relatively smaller moments. And in fact, if you can get perfectly balancing forces, you can actually have zero moment acting over the arch. So the reaction forces which you discussed from this arch, when it's loaded, are going to result in a horizontal thrust, as well as the vertical load we've already talked about. And this horizontal thrust is also going to have to get resisted by the rest of the structure. So let's draw the rest of the structure out in plan. We've got the horizontals coming down like that, and the arches span across. Pin them in the middle, either side. Then the direction of the thrust is going to be the same as this direction. So it will come out of the structure like this. And that thrust is going to have to be resisted by these members. Now we can break it down into two components of force we know about from before. So we've got a force going in this direction, this way in the structure, which is going to be resisted by this member going into tension, because it's the most direct, easiest way for the structure to carry that force. And then we've got another component orthogonal to that, which is going to want to bend this whole section. So this section is going to have to resist that force by going into bending. Now there's one more final force which is going to have to be resisted by the structure, and that's going to be the result of this bending, because the column, which we can draw in plan again, is going to have to resist the torsional force from this bending around it, and that will take the load finally into the ground.